So hello, everybody. I think we're going to get started. It's a little bit after the hour. I can see we're losing more people. That's wonderful. So first of all, thanks, everybody, for being here. It's nice to see that some people are interested in scalding and have managed to stay this long. So before we start, actually, so I can figure out sort of how fast I should go, there's a lot of content here. Can I get a show of hands as to who is comfortable in Scala? Okay. And what about, who here has used scalding? Okay. All right. So then I'll go pretty slow, and we'll just see how far we can get through this. Without any further ado, I'm Justin Coffey, Sofiane Jama, and we're going to talk about what we've done with scalding. So this isn't a talk about like the right way to use scalding, but it's really about what we did with it. So let's get going. So some of you who've used scalding might have had some difficulties getting going with it outside of using the very standard stuff, and you might think that you're just wasting your time and it's really hard and painful. It is hard and painful, but it does get better. So a few words on scalding. So it's basically just a way to write MapReduce jobs in a functional way. So using a sort of Scala collections API. It's written in Scala, but it actually ends up just being cascading underneath. So who knows what cascading is? All right, that's good. So for those who don't know what cascading was an early attempt to abstract away a lot of the awful boilerplate and rote operations that you would need to do MapReduce. So it's just a thing on top of pure MapReduce. So actually what we're going to be talking about today is the typed API of scalding. So the way to look at this is all the way on the bottom you have MapReduce, and then you have cascading, and then you have the Scala fields API, and you have some extra sort of sugar on top of all that stuff that gives you the type safe API. So that's what we're going to talk about. So this is directly from, I think I just cut and pasted this from the GitHub of scalding. You know, it's simple word count. It's sort of the canonical example of how to do, of what you're supposed to do with a MapReduce job. But that's really not our reality. So sort of a slightly changed version of that is more what we have to deal with, which is we have really, really big logs. It's not, basically a word, right? It's a lot more than just one field. We have lots of dimensions, so we're going to be grouping on maybe a dozen values, and we're reading from various places and writing to various places, and it's not terribly standard all the time. We're a big established Hadoop shop, and that means there's a lot of legacy, and so things can be quite varied for us. And then also, when you first get going, you start getting like wacky things like arity of class, whatever doesn't match what you're saying, and it just seems completely ridiculous. And so this is the sort of thing that you end up running into when you're not doing just the how-to. Right, and so then you dig and dig and dig and dig, and you find out actually why you got that exception, and you're like, Jesus, I just spent 3 hours doing that. Maybe somebody could write this up for you. So I'm hoping that actually you guys will get a little bit of a takeaway from this. I'm hoping I'm not going to scare you away from scalding. If you have MapReduce work to do, I actually think it's just about the best option. So hopefully this isn't going to scare you away. It's just going to give you maybe some hints on how to work around your problems as well. So I'm Justin Coffey. I run the analytics team in R&D. So that means I don't do analytics. Actually, I provide the infrastructure, data, and systems to the people who do analytics. And Sofiane is in the team, and he is doing a lot of the data engineering, both batch processing and streaming. So this just gives you a little bit of idea of our scale. We have 2 Hadoop clusters, around 2,000 nodes, around 30,000 cores, lots of terabytes of memory, and lots of petabytes of disk storage. And the ingest rate is on the order of about 25 terabytes, and that's about per day, and that's basically about 50 billion records a day. We also, this is a slide I use in the US because we're always recruiting, and in Paris we get 7 weeks of vacation. So anyway, here maybe, I don't know, how much, who's from Dublin-ish? How much vacation do you guys get here?
Between 20 and 25 usually.
Yeah, see, it just doesn't work here. All right. So before we get down into the nitty-gritty, I just want to give you guys some background on what we're trying to accomplish with scalding. So I think it'll help a little bit more as we get into the details. So this is what we're trying to do. We have to build out about a 20 terabyte data warehouse that we're going to do really, really fast operational reporting on. We're trying to get sub-second queries out of that data set when we're querying it. Everything goes through Hadoop, and all of it ends up in, or well, the actionable subset of that ends up in Vertica. Vertica, for those who don't know, is a shared nothing MPP database. It's columnar. It's all those sorts of fancy things. It's one of the innovators, originators of that whole paradigm. So scalding, what is scalding doing for us? Basically, it's just doing all the ETL work, right? We do it for really stupid things, like we have 6 records to transform, and we're going to do it in scalding. And the reason we're doing that for the really big stuff and the really small stuff is simply to centralize logic. We can just look at the code quickly. Everybody knows what we're looking at, and we can quickly, go through code review and whatnot, and everything's in one place. So now there's a slight pitch for some of our own in-house work. For the scheduling part of this, so when you're doing this kind of thing, you don't just have one scalding job, you have a lot. You need to make sure those get executed in the right order. And so we have our own in-house scheduler that we've written that's also in Scala. Its code is config. We're actually a relatively opinionated group of engineers. We don't like writing XML. We don't like big, nasty infrastructure, so we tend to do these kinds of little projects that fit nicely into our paradigm. And so Longustine allows us to write code to describe what we want our jobs to do. It's also easily deployed because it's running in Finatra, which is a sort of a standalone web app environment, similar to Play or other things like that. Also of note, we expect all of the nodes in the graph to be idempotent, so that we can replay and we can be safe about the execution of our graph. So very quickly, this is the UI. There's the graph, options and things like that. You can zoom in on the graph. We can figure out what the state of our job executions are. We can see that there's some red spots here. That means that there's problems, there's gaps here, failures that we have to go investigate. And then actually, so this is the DSL. This is how this is our, completely useless example. Hello world. So you just describe a job. It's going to have a task which takes context and spits out an echo task, which does probably what you might expect it would do. And there's 2 things here. There's 2 hello and world. And what we do is at the end, we just say that world depends on hello. And then to launch the whole thing, you just do that. So that's Longustine, no more sales pitch. So moving on to file formats. So I mentioned earlier that we have a legacy environment, so we actually consume a lot of JSON data that's gzipped. And so there's not a lot of stuff out there to help you do that. We consume it in what are called pale files, which is also something you really should never do. It's just what we end up doing. We also use Parquet quite a bit, and we have some intermediate results that are just purely text delimited because that helps us get into Vertica more easily. So a note on finding data. So lots of shops these days are using hcatalog or other sort of Hadoop ecosystem components to do data location and data dictionary stuff. We don't have that for various reasons. And so at Criteo, every single job in theory, has to roll its own data location service. So when you fire up your job, you're going to give it some input, and it needs to go figure out where to read the data from. So in our world, we have to hand roll that. So the type-safe API, why do we use it? Well, because it compiles, and so therefore it works. That's obviously true and false, but it is really, really helpful when you're dealing with very, very big logs, wide logs, to be able to be certain of the types that you're dealing with in between your job steps. Is just incredibly helpful. We have old legacy code that's in pure cascading, that's completely stringly typed, and the maintenance on that versus the new code that we're producing is completely a different story. Right, so we have lots of logs that have 23 fields or more. We're also on Scala 210, so that means that we can't take advantage of tuples that are of any size. So that ends up meaning that you have to write your own tuple setters and converters. Just a word on job tests. So scalding provides you with a testing sort of helper, and it's called job test. It basically just tests the core logic of your job, but actually what you find out when you're doing work in scalding is that, especially the type-safe API, is that all the hard stuff gets pushed off to the edges, right? So this is where you're reading something out of some sort of external source, and you're trying to get it into native Scala types. And that translation layer is where lots of things are going to be problematic. And job test doesn't really test that. So it's just testing your core logic. Or it's not designed to it. It's just designed to test your core logic. So that's the context. So now we're going to get on to actually what we did. So if you've been following along, you've maybe figured out that at least a few of these things, that we need to be able to find our data, we need to be able to convert it, we need to be able to serialize it and deserialize it, and then we need to be able to have a source and a sink, which is just sort of the way that scalding allows you to consume and write data. So we came up with this idea. We worked off of that, and we just came up with this formalization, right, in a trait, in a Scala trait. So for those who don't know, Scala traits, just call them kind of like interfaces. It's a little bit different, but fundamentally it is that. But the nice thing about Scala traits is that it's an interface in which you can partially implement things. So it's somewhere between an abstract class and an interface for Java programmers who aren't familiar with this. Don't worry too much about the implicit stuff. We'll talk about that a little bit later. But so you can see here that we're going to declare a tuple converter of a given type, a tuple setter of the same type. We have to have this fields thing, which is just an internal cascading business. Then we have our partitions that we're going to declare for a given partition key. We're going to be able to give a sequence of folders. And then for that same partition key, we're going to be able to have sources and sinks. So let's talk about writing tuple converters and setters. It's basically like old school JDBC code, right? You're doing some really nasty, unsafe stuff, and as you're converting things from a tuple entry into your type, and vice versa, from your type back into a tuple entry. Yeah.
If you were on Scala 211, you wouldn't need those, would you?
In theory, yeah, we haven't tested that, so I just don't know. So yeah, so yeah. So to me, that just reminds me of working with JDBC, which is not really why I think I don't think I should be paid for doing that. So we wrote some macros to do that for us, and it just becomes as simple as that. So you just say a scalding tuple setter for some type, a scalding tuple converter for some type, and scalding fields for some type, and then you just get those things. For those who don't know about macros, it's compile time reflection is a good way to vulgarize it. So then we need to have sources. So this is a tab separated or text delimited source, again, for a given type with a given key, because we're going to actually start working with partitions here at this point. It's a self-type, again, don't worry too much about that. That's just sort of how you can kind of ensure that you have you can do a mix-in of this trait with other traits, and you can stack things. But just gloss that over. So sort of tying that whole thing together, we can see now that, we're going to just use this example class, right? It's a 3 fields, so in theory you wouldn't need to actually use any of this because you could just use a case class in Scala and not have to do all this sort of boilerplating stuff that we're trying to get around, but for the purposes of an example, it's useful because it's concise. So we've got an events class, timestamp name and events, a time key as a root, which is what we're going to use to declare what sort of the base path is of all of our data, and then this sort of variable here. So so we're going to declare an object, which is the companion object of this guy. So again, that's sort of Scala ease. It's sort of just a global object for this type. Again, so we've got our scalding type of events and time key, and we're mixing in our TSV sources of events and time key of the same types. And so now what we're going to do is we're going to write out our little implementation of the tuple setters and converters and fields. The sources are done for us because it's here. And now what we're left with is having to implement our partition lookup function. Does anybody have any questions to this point? I'm trying to go a little bit quickly because we have a lot of content. But if anybody has any questions, please just raise your hand, interrupt me, whatever. Okay, great. One of the nice things about, we're going to see this a little bit later, but one of the nice things about the companion object of Scala is that we can start putting some implicitly available things in this companion object, because that's in the lookup chain of the Scala compiler. When it finds that it needs something of a certain type, it's going to go through sort of it's going to look through various scopes until it gets something that fits what it's looking for. And this allows us to get rid of a lot of boilerplate later on, and you'll see that. So now that we know a little bit about how to formalize things, let's write a job based on this events type. We're going to write the job from an events type into an event sum. And our event sum here is just time and events. So this is a counter, and this is some sort of bucketed time. We're not going to really worry about the details of that. So a job would actually look like this using our sort of system. So we've got, this is the scalding API. We're going to map something. We're going to sum it. We're going to take the values of it, and we're going to write it out someplace else. And so these are our sources, or this is our source, and this is our sink. Some of this stuff you might have been questioning, like where it came from, right? We're talking about like typed args, from events, and this magic sum by key. So where did all that stuff come from? Also, you see that there's this new trait that we've mixed in, time job args. So there's a little bit of behind the scenes work going on here as well. So the time job args trait is taking the scalding args object, which is just basically this bag of stringly typed stuff. Just consider it the equivalent of a command line argument string, right? var args. And we're going to take that args, and we're going to, as quickly as possible, we're going to turn that into a typed argument type. So this allows us to get some failed fast aspect of it, and allows us to also do some reliable operations that would not necessarily be fail fast if we hadn't created that type early on. From events, that function is just mapping events to event sum. If you remember, it's from events sum dot from events, so it's just sort of a mapping function. Very simple. And sum by key is a scalding aggregator, and it needs a semigroup with ordering of the data inside the set that you're trying to aggregate. So some of you might not be familiar with semigroups and monoids and this sorts of things. So a semigroup is a mathematical set with an associative binary operation. It's also a monoid without a zero value. So it's sort of a formalish definition, so don't freak out about that. Not all of us are steeped in category theory, and myself included. So basically what you need to know here is that in scalding land, well actually algebra, a semigroup of T is just a thing that describes how two T's should be added together, and that's it. So you've got two T's, we're going to do an aggregation, we need to figure out how to combine them. That's it. So we're going to go ahead and implement a semigroup now. And what you can see is we're back in our companion object. And we've got an implicit ordering. And going up here, you see we've just got these two things. So what are we going to order on? Well, we're going to order on time. We're not going to order on events. That doesn't make any sense because the events are the things we're going to combine. So you can see we've just declared that the ordering is going to be on the milliseconds of the time type. And then this is really the nuts and bolts of a semigroup here. And you see we're just implementing a function called plus, the left side plus the right side. What are we going to do? We have a little requirement that the times are equal. And then we're just going to copy the L object and add the right events into the L object. This is sort of, again, Scala syntactical sugar that we get to use. I'm actually kind of cheating here because that's stuff you get out of a case class. And well, I did declare as a case class, but we're talking about why we're using this because we can't use case classes. So what we end up doing, we do this is exactly what we do in production code, but we just implement copy ourselves. And then we have to add the map function in, which is simple, stupid. You take a source events object, you create a new event sum where you're just copying the source and the timestamp and the events, and you're throwing away, I can't even remember what the type or whatever it is. You're throwing away one of the values. So if we go back to our job, we can take a look at the progress that we've made. You can see that this has been implemented, and our sum by key is now going to be functional because we have our semigroup and our ordering. So now we need to parse arguments. I'm sorry, this is a little bit dense for this kind of a setting. So basically, we have a new trait that we're introducing called a typed Args parser. And it's going to take Args, and it's going to turn that into a type. This is not the same type of the object we're trying to serialize. Or process. It's the type of the typed Args that we want to get out of this. So here, in this case, we're going to have time Args as our type. And you can see that here, and we've just implemented it. And all we're doing is we're taking the Args object, which is, again, Scalding's Args object. And we are taking the stringly typed API and turning it into a strongly typed time Args object. So now we get to expose that as a typed Args value inside the class, inside our job class. And so that's just this type here, or this trait, sorry. And then we just, so we can get rid of some of the verbatim here. We just create this trait time job args, which is the thing that I introduced way back at the beginning. So progress so far. So now we have our trait there that we're mixing in, time jobs args, which we now know exposes typed args. We have our mapper, we have our aggregator, and then we're also actually using the same typed argument for figuring out where to write our events sum out to. So going back to partitions, right? Partitions are just a set of folders, right? That's all it is. And so what we're doing is we're taking a key and we're turning it into a sequence of folders. And just if you recall, at the beginning we talked about a time key, and then I talked about time args, and they're exactly the same object definition. So we're just going to stop talking about a time key, and we're going to start talking about time args now. So time args is partition key. So here, just to be complete, we're implementing this whole thing, and this you can see here is really unsafe. So this is a work in progress, what we're doing, and you can see that there's good chance that there's a typo there, things like that. So this whole thing isn't completely wonderful and complete done, but this is actually what we do. So going back to our job, now what we can do is we can walk through this a little bit more, and you can see where the implicit stuff is happening. So when we're reading from disk, we need to, or from our source, we need to be able to convert what we're reading into a Scala type, and that's happening by implicits, right? Because we have the events, we've declared that events in its companion object has an implicit converter of type events. And behind the scenes, this type pipe from declares that it needs implicitly that converter. And so that just happens for us. Scala takes care of that. This is also done implicitly. So if you look at the signature of this function, it requires a semigroup and an ordering implicitly. And again, that's available to us because in the event sum companion object, we declared that implicit. Likewise, finally here, we have the implicit setter. We're doing exactly the same sort of resolution. So And we're going to talk quickly about idempotence. So basically, it just means we can do something multiple times and bad things won't happen. There's a little reference. We had this little discussion the other day. There's like the mathematical meaning and the computer science meaning. And we're just talking about the computer science meaning here, which just means that we can do this thing as many times as we want, and we're going to get the same output, or we're going to get predictable output, and nothing bad is going to happen. So we're going to make the job idempotent now as well. Sorry, yet another trait. And so this is just an idempotent job trait, which actually just implements some boilerplate inside of the job itself when you actually run the job around the main that you normally need to implement. It implements the main for you. And so you have to declare the class. We could probably do this through macros, but whatever. And you have to also say the partitions that you need to clean for the incoming var args. Basically, this isn't var args, but you can imagine that that's where it's coming from. So for the input arguments at the CLI level, what are the partitions that we're going to need to clean? And so you can see we're just doing some of our strongly typed stuff here to get those args into a time args object, and we're spitting out the partition. We're using the partitions function for our target type to get the set of where we're going to write out to. So the job fires up, and we know immediately where we're going to write out to, and we're going to go look over there. And in our case, we're actually going to clean up everything. We're going to do an HDFS RM. But you could quite easily just say, I don't want it to clean. I just want to see if something's there. If something's there, I'm not going to do anything. Yes?
Is the idempotent jobs trait a scalding one or yours?
That's ours, yeah. All this stuff is ours, actually. Yeah, there's nothing besides just job, which is scalding, of course. So if we go back to the job a little bit, if we had to include all that boilerplate, and I've shortened it here, right? It would just be this gigantic set of quite a lot of code that you need to write just to deal with like 4 lines of actual logic that you're trying to do. And this is bad for lots of reasons. Obviously, there's code duplication here. You could factor that out too. You could do this all manually every time, right? But by formalizing it, we get a consistent way. Like I get a new hire in my team. We can show this person this formal system, and they're immediately operational. They can also just look at the definition of a job, and they're immediately understanding what's going on. Because this logic, this is a gross simplification of the things that we do inside of our jobs, and it can be very hard to read this logic and figure out what's going on, and you don't want all this noise around. So taking all that in, again, the type-safe API pushes the unsafe parts out to the edges, the converters and setters. We formalized a lot of the boilerplate into a trait called scalding type. And we try to get as quickly as we can to a fail-fast environment by converting the command line arguments into a type immediately. We have an idempotent job trait so that we know that once that's implemented, this job can be executed as many times for the same typed args value key safely. And then in the end, you're just looking at job logic when you're doing code reviews or when you're thinking about your job. You're just thinking about the logic. You're not thinking about all the stuff that is actually going on behind the scenes. So that's the end of the functional part of this talk. And actually, I'm going to hand it over to Sofiane, who's going to give you a little bit more details on what scalding is doing behind the scenes, and also some of the optimizations that you might end up doing if you're using scalding. So with no further ado, thank you.
Yes. Let's take a more complicated job than the one we used before. Basically, we have one source of events that we want to enrich with other dimensions. So we have introduced the join. And if I take it very shortly, we group it by some type of events. And then we want to join it with the weather forecast, let's say, depending on the time. So we group it by type, then by time to, for example, to have it by hour. And after that, we join it with another source, and we map it to the final result that will be synced in HDFS, for example. It's very important to know what's under the hood, basically, because as Justin said in the beginning of the presentation, you have scalding, which is over another framework called cascading, which is as well on top of MapReduce. So it means that there's a lot of stuff happening, so you need to know what's going on when you run your job in production. So if we take the job, what's happening? Do we have, as a result, 4 jobs? Because obviously when you code the scalding jobs, as a result you have actual MapReduce jobs. So one piece of code can generate several jobs. So do we have 4 jobs as a result? When we have a group by, as you have mappers taking data from the source, you need to group them, so you need to take all the results from all the mappers in a single, as a single result. So it means that generally a group by triggers a result, a reduce phase. You have another group by triggering another reduce, a join with another source. This source uses a group by as well. So normally you should have 3 jobs, and as we need to merge all the sources with all the mappers, basically this this source needs to be joined with the results of the 2 group bys, so it triggers a 4th job. Actually, no, because scalding provides optimizations, especially the reordering of operations. We have the 2 group bys following all the sources, so the reading of the source, meaning that probably we don't need to trigger a reduce as we already have all the data from a single source. So it means that the two jobs actually are within a single one. With this piece of code, we have 3 jobs. Can we optimize it? We can, and we can take off 1 job. So what happened? We had the 2 group bys, the join with another source. We removed the 2 group bys. We mapped the source as a key value pair so that we can emulate the group by. We join it with another source that is actually the very first job that will run on the cluster. You join it with the other source, and you do all the operations on the mappers using another operation, a computation that can accelerate your jobs, that is sum by local keys. So if you use a sum by keys that we used during the whole presentation, the sum by key is done only on the reducers, because we have the group by and then the sum. The sum by local keys starts with does the sum by keys as well on the mappers. So you have this this operation twice. Once on the mapper, so you have less data going to the reducers, and then on the reducers as well, you have the sum. So we have 2 jobs and a small optimization. So can we go down to 1 job? No, not with this code. Because another optimization we could have think about would have been the hash join. We do a join between events and the dimensions, and the dimensions can fit in memory. So then we can use a hash join. Unfortunately, this hash join leads to bad results, because when we use a hash join, it means that this source is copied, broadcast in Spark, that's the same, to all the mappers. So we don't need to reduce, to use it in the reducers. Everything is done on mapper because it's copied to all mappers, so no need to have a reduce phase to consolidate all the results. Especially because we use the sum by local keys, the other optimization we used before. Because in the whole code, we don't have any mention of using a reducer. We don't need it. This is done in memory, in all mappers, and as well, this is another operation on the map side. So it means that we only have, instead of having one job with a map phase and a reduce phase, we have one job with only a map phase, meaning that what we output in HDFS are actually partial computations. We still need to aggregate them after. Otherwise, you get bad results. And why we want to know how many jobs we run and why do we want to optimize this? It's simple. It's because you may face latency issues because you depend on the scheduler. Let's say if you run your jobs in a pool, the pool is full. You want to have as few jobs as possible so that you can finish your job very quickly. Let's say you have 4 jobs. All the 4 jobs are go to the pool. So it means that you can wait a long time before having all the 4 jobs executed. Therefore, it's really, really important to reduce the number of jobs that will come out of your scalding job. Some other performance hints. Here, for example, we have an example of a job we did, one of the steps from one of our jobs. We have only mappers, the fastest 32 seconds and the slowest almost 20 minutes. And if obviously you want to have all the mappers finishing really quickly, basically at the same time, so that you don't have any wait and wasted cores. So to do that, you can distribute evenly the data on the mappers. Unfortunately, it's not always possible, especially when your data, you have very, very small files. So when you have small files, what you can do with other mappers that have big files is to output intermediate files. Let's say in the middle of your jobs, you call shard with a number that outputs for all mappers very small files, this number of files, so that in the reduce phase, you can, first of all, the mappers can be really quick, much more, they can run quickly, and in the reduce phase, you have less data instead of having very huge data, huge files going to the reducers, shuffled to the reducers. So you save as well IOs. For the reducer, a very simple trick. By default, scalding uses only one reducer. So you really want to have more reducers to have so that you can finish your job really quickly. So it's a balance between, because the reducers, if you use a lot of reducers, you will have more files on HDFS, and if you have many files on HDFS, the other jobs, depending on those files, will have much more mappers. And obviously, you want to have your mappers using, let's say, the block size of HDFS, so that you really take your you use your resources in the best way. And last, that's very important. It's very simple and it's obvious, but you really need to check the counters. Especially, for example, in some operation in Scala, you may have GC issues. You need to check as well your speed records to know if you have too much data on your mappers. So if you have more than 100% of records spilled, it means that you have merge sort operations. So a lot of I/O disk, and you want to optimize this. The distribution of data between mappers, as we said, using a right data format to optimize as well the reads and the writes. So very important to check all the counters and everything is available in the UI, in the Hadoop UI.
Yeah, don't ever consume gzipped compressed JSON. That's really bad.
So yes, we're hiring. If you're interested in working with scalding, we have as well a lot of other frameworks. So if you want to work with large volumes, you're welcome. And that's what we have every day on our rooftop.
Well, when it's sunny.
When it's sunny, yes. So thank you. one last thing. I'll let you talk about this.
This is a little plug. So anybody who's in Paris on and around the 26th of May, please come by and see us. We have an all-day sort of open house where we've invited some Google engineers and folks from Mesosphere and Spotify as well. So we'll be talking. A lot of other teams at Criteo will be talking about what they're doing. Lots of really interesting stuff on Kafka, on Hadoop, on all kinds of stuff. We'll be going a lot deeper into that 20 terabyte data warehouse as well. Lots of fun stuff. And then you'll get some color from Google, Spotify, and Mesosphere. So it's effectively free as well. So just if you happen to be in Paris.
Thank you.